So first we got Harry Roberts. There you are, Harry. I'm gonna make some space for you on multi-chain economy. If I got that right.
Autonomy, yeah.
Autonomy. Oh, you're right. It's right here. Yeah. I need to increase the size of my screen. There you go.
Sure. I'll speak through these if I can. It'll be easier. So, hi everybody. I'm Harry. I'm a product manager at Oasis Network. I'm working on OPL and Sapphire. And the reason I'm here today is because scalability is a big problem, and I think smart contracts should be smarter. And there's always going to be more chains and more tokens and sort of death, taxes, and haircuts. But let's start by sort of trying to define scalable. And I think of it as a battle sort of between humans and machines to impose order, which is this sort of global linearization problem. If we look at the ideal functionality, so everything must happen only once with instant visibility of everything else. It's final forever. It can never fail, and nothing's ever forgotten, which is a bit of a big ask. But in reality, yeah, this doesn't happen. So we're all human. If the system's big enough, for example, then everything's failing all of the time, and there's packet loss and errors and everything else, right? So failure is the norm, and it's just something we have to live with. And it's only failing because of communication. I'm not sure if you're aware of Metcalfe's law, but it's assumed that the total value of a network grows proportionally to the square of the node count, and that's because of communication. And of course, we need Erlang's theorem too, because you can only talk to so many different people at once. And in short, the best case scenario is n squared, because everyone's talking to everybody. And that's also the worst case, because everyone's talking to everybody. And this means that, well, while the cryptography maintains integrity, because there's lag and errors, and the nodes need to communicate with each other, and failures happen, we only know what nodes tell us. And over time, we sort of eventually settle on the same answers. The key is like over time, but sometimes it forks or rolls back, or reality happens. So let's look at some examples where we have Gaspar, our little ghost, who's chasing transactions that depend on each other naturally towards our Pac-Man of finality. And he has to decide which ones come first, which is usually a straightforward problem. And if we want to handle more transactions, you could just add another chain. So add another chain, now we're parallel. N chains is n times as many transactions, which seems an easy way to scale up. But all the chains are different. So they process a different number of transactions per second. They've got like different finality semantics. And we thought we could just have like a bigger, faster chain that just decides what's final and everything. But once it says it's final, that means nobody else can roll back. There's no possibility of having forks. And that's not reality, right? You can't just dictate all of this to everybody else. So the reality is, well, we have to communicate between these different chains. And you can't expect people to stay neatly on their chains, because otherwise we just create the ultra mega blockchain that does a bazillion transactions per second, and everybody uses that, and that scalability is sort of solved. But when I'm talking about eventually consistent, this is what I'm trying to get at, which is there is no sort of neat finality line that's sequential. And it's a sort of a polychain interdependent world of different transactions that are all happening at the same time, and they run wherever the assets happen to be. But then we get into the real world again, and everything's on fire, the rugs are getting pulled, but it's highly concurrent, and it's parallel, and it's scalable. And even though it's failing all the time, it's also incredibly fault tolerant. And it's so much more valuable than any one chain on its own. But the reality for me is that you've got this game of hungry hippos of all the DeFi users who are trying to get the transactions and get their orders in, versus me on the back there covered in wires, just trying to plug all of this together and make it work. So realistically, we need to sort of try and make some shortcuts to overcome the problem of everything's connecting to everything, communication errors, and so on. And we can sidestep some of these common gotchas, so we can reduce the number of state updates, which means that the network doesn't have to agree on what's being updated so often. We can use proofs like ZK snarks, or we can use trust and summarization to reduce how much data is communicated. And we can use statelessness and eventual consistency or idempotent operations. And that's kind of where Sapphire comes in. So Sapphire is our confidential EVM. And a confidential EVM is secured by the Oasis network. So it uses a verifiable compute layer together with a secure isolated key manager. So unlike other confidential EVMs or confidential networks, we don't have one key that secures the world. We have our own key manager, and every single contract has to request to decrypt stuff. But generally, that means the contracts, they can't see your secrets, and there's no message passing overhead if you look at these cross-chain protocols. And it's fast, and it's programmable. So we're using Intel SGX, but at the moment, we're still looking for other options, but it's kind of the sweet spot in terms of trust, reliability, But for the purposes of this talk, I thought let's think more generally. So let's look at what trusted computation can do versus the other technologies like ZK snarks. So we have some building blocks, like the contracts can have their own secret state. You can have cryptographically secure random numbers that, again, they're private to just the contract. You've got signing and encryption. And if you don't modify the contract storage, then everything's free, right? It's like view calls on Ethereum. So what can I use it for, though? Well, anything. So we have this big overlap with ZK snarks, with MPC, distributed key generation, and EVM, but with a different set of trust assumptions and with different trade-offs. If you're mindful of these trade-offs, you can take advantage of it in some really interesting ways. And one of those is to turn sort of very complicated problems into quite simple ones that aren't easy to do trustlessly. And that's mainly because the contracts can have their own secrets. So if we look at an example of what happens if you let a contract generate an Ethereum key pair. So the contract has a key pair, only it can control it, and with that it can act, so it can sign its own transactions, it can sign them on its own chain, or it can sign on other chains. So we have an example of a contract that does gasless transactions by creating an account, giving it some gas, and then signing transactions that the user puts back into the blockchain. Or it can arbitrate, so it can act as a trusted oracle. That's for other contracts on other chains, or just between users to sort of mediate like a swap or an exchange. And this can radically simplify protocols. So because it's free if you don't change the state, you can act as a trusted coordinator. And most of the time it's for the cost of deploying the contract, unless you need some sort of state synchronization. And that means it can shortcut sort of complex multi-chain, multi-phase commitment algorithms because it is its own actor and it can have its own sort of degree of finality. So rather than 10 messages across 3 or 4 chains, you can have 2 messages on one chain that enforces this across lots of different chains. And that's kind of like what a ZK snark could do, but it's just a different concept. We can even do recursion. So like recursive snarks, you can pass its own signed or encrypted state back to itself, usually for free as well. The limiting factor for scalability, though, is how fast can state updates be distributed and then agreed on. But if you have a purely functional stateless logic, you can scale out using the actor model, where the network ends up being the computer. That's because state updates are less frequent, so everything can run high concurrency and highly parallel. So there'll be much lower communication overheads, and any node can give you an answer immediately rather than having to wait for the next block to be committed. So an example of this would be running a Bitcoin-like client entirely statelessly in view calls. So the contract can sign that it's verified a block, and that signature can be passed back to the contract. And then, when verifying the next block, it keeps track of how many blocks it's verified in a row and the cumulative proof of work. So that means if you trust the contract's key pair, you can use EC recover, for example, on any other chain to verify that a Bitcoin block header is valid and it's had a certain amount of proof of work without having to run a Bitcoin-like client on every chain that you want to work with. So again, you can do this with recursive ZK snarks, but EC recovers a little bit cheaper, snarks are a bit more expensive, and it's a trade-off, but you have to trust the contract. So as we move on to sort of multi-chain contracts and towards autonomy, so if a contract has its own key pair and it can sign for transactions on other chains, and depending on the protocol, again, you don't necessarily have to pay gas all the time. And with a lot of careful design, the problem is you need to be aware of the state of the other chains. So the gas price, whether a transaction output has been spent or not. But you can have a contract that operates over 10 or 15 different chains. So the transactions are happening on these other chains, but it's all being synchronized through Sapphire and Confidential EVM. The problem is that the contracts are doing everything in isolation. So it's very difficult if the contract's blind. It hasn't got an oracle. It's got no knowledge of what's going on other chains because it can't access the internet. And sometimes it's not even sure if time has necessarily passed. So, of course, in the case of like the adversarial model, you've got the malicious validator that could try to trick your contract. But it has its own keys, and it can update its state, so it can move forward. And there are some interesting design sort of problems around that space about how to have a contract that can operate across all these different chains and potentially have adversaries as well. So with a little bit of logic, though, you can figure out all of the possible states that you could and can't be in. And you can rely on users to pay for your gas because it's in their interest. And you can think of them as worker bees. So while the contract is in isolation, it's blind, you've got the sort of game theory of the users are going to do what they want to do. And you can treat them like worker bees. So to pass messages across chains, you can get them to create proofs for you. And of course, because the keys exist on Sapphire, the state of contracts on each other chain can sort of help keep a distributed protocol coherent. So if you have your contracts deployed on lots of different chains and they're all following your state model that depends on some contract being able to sign, then you can maintain coherency. Or you can use the contracts like super smart state channels. So if we think of state channels as being the first innovation to remove the number of transactions that you have to commit to chain because you're just going back and forth between the different participants. But with a state channel that has its own keys, that can have or it can verify other state channels and it can sign transactions for people across multiple chains. You still have to rely on the participants of each state channel to do all the legwork, but it's offering sort of safety and programmability and a certain level of finality. So an example of that is if you want absolute instant finality, you give a secret key to somebody because it can never be revoked, it's instant, and you don't have to wait for block confirmations. But that's a double-edged sword at the same time. So I'm not sure if how contracts with keys could evolve, or if there are sort of use cases that people can come up with, but there's a long history in computer science studying automata. And for 1 billion new devices that get made, there will be many, possibly hundreds of little networked programs that are all talking to each other via servers and users and Bluetooth. And a lot of the RF spectrum at the moment is full up with little contracts and state machines talking to each other. So the real world sort of operates in this way, where they don't necessarily need to know about each other. They don't need to know about the global state. They don't need to synchronize with a giant blockchain. They just keep going in their own little world because they're not doing big things. They're just sort of tiny little cogs in the machine. We're still going through a Cambrian explosion. So not just in the blockchain space, but in all aspects of technology. There's lots of stuff that's not ideal, and everything's made of building blocks. So they seem really advanced at the time, but in retrospect, they're quite simple. So if we go through a few, which is TCP is 50 years old now, ARM processors are 40 years old. HTML is 30 years old. Elliptic curves were being standardized 20 years ago. Blockchain was gaining traction 10 years ago. And ZK snarks, after a lot of research, started gaining traction about 5 years ago. So maybe we can think about confidential EVM as being one of these enabling factors that does something that none of the other tech can do at the moment that could continue this sort of growth and explosion of new capabilities and technology. And of course, I'm interested to see where this is going, but I got a feeling that in maybe 10 or 20 years, whatever happens, it's going to surprise me. And in 40 years' time, everything's going to be pretty confusing. Because it's just like the beginning of autonomous contracts. So hopefully they'll scale. Hopefully they'll be everywhere. I think it's inevitable. But some of the building blocks that let contracts be autonomous aren't quite there yet, because everything's designed for smart contracts rather than smart autonomous contracts. So like interoperability at the moment, even with smart contracts, is really annoying. Possibly like autonomous contracts could make interoperability a bit simpler for the users, because they would be doing what they know to do without needing the user to know what they're doing. And there's lots of dApps for a lot of people, and they're trying to do big things. But of course, we then need to layer upon that of like helper services like bridges, data APIs, and that sort of means that every blockchain that we add, we need hundreds of, possibly thousands of times more infrastructure, where if it goes down, the contracts and the chains become useless almost instantly. And maybe there's a way of having autonomous contracts that mean you don't need all of this extra infrastructure because they're independent. And yeah. But anyway, shoot, I'm almost done. We're running a hackathon tomorrow, so hopefully, if you would like to explore some of the ideas about contract autonomy and maybe innovate, I'm here to help as well. And we have up to $30,000 in prizes and sort of some follow-on grants. And yeah, I mean, everything from confidential storage to the idea of autonomy, contracts with keys. They're interesting things that are worth looking at. We're going to have sort of 25K in follow-on grants and prizes across 4 categories, so you can find us by looking for the Oasis Rendezvous or go to oasisprotocol.org. And thank you, that's me done, just in time.